Today's episode dives into three very different frontiers of AI: safer optimization for training massive models, the hidden engineering behind modern coding agents, and a new way to plan with latent world models. We'll unpack how CLion sharpens Lion's efficiency and generalization, why Claude Code is mostly a carefully designed execution harness rather than just a chat model, and how hierarchical planning can dramatically improve robot and maze performance. Together, these papers reveal a bigger story about where AI is becoming more reliable, more capable, and more practical. Let's explore the first paper, CLion Efficient Cautious Lion Optimizer with Enhanced Generalization. This paper introduces CLion, a cautious variant of the Lion optimizer that replaces unconditional sign updates with a thresholded rule. Use sign CT when the smallest non-zero coordinate magnitude in the gradient estimator CT exceeds NIU, otherwise fall back to the raw estimator CT. The authors analyze Lion's stability for the first time and prove an on-average generalization bound of 0.1 tout, where tau is the smallest absolute non-zero entry in CT, n is sample size, and t is iteration count. Sign SGD inherits the same bound as a special case of Lion. Because tau is typically very small, this yields a potentially loose guarantee. CLion removes this dependence and is proven to achieve 0.1n generalization, matching SGD and SGDM under the same stability framework. On the optimization side, CLion retains Lion's non-convex convergence rate with an expected 1 gradient norm decay of O square root D T 1,4 under stochastic non-convex smoothness assumptions. Experiments on Wikitext 2 and Wikitext 103 with 7, layer and 2.1, layer transformers, plus CFAR 1.0 with ResNet 1.8, and Tiny ImageNet with ResNet 3.4 show CLion outperforming Lion and RLion on training loss, test loss, perplexity, and test accuracy, while using the same memory-efficient sign-based update whenever gradients are sufficiently large. Let's explore the second paper. Dive into Claude Code, the design space of today's and future AI agent systems. This paper reverse engineers Claude Code v2, 1.88 from public TypeScript source and contrasts it with OpenClaw to map the design space of modern coding agents. Its central finding is that Claude Code is architecturally a thin React-style while loop around the Claude model, with roughly 1.6% of the codebase devoted to decision logic and about 98.4% to deterministic harness infrastructure. The model reasons, but the harness executes, filters, compacts, persists, and recovers. That harness is organized around 5 values: human decision authority, safety, security, privacy, reliable execution, capability amplification, and contextual adaptability, operationalized through 13 principles such as deny first escalation, defense in depth, append only state, graduated trust, and transparent file-based memory. The system's distinctive mechanics are a 7-mode permission stack, including plan, default, accept edits, don't ask, bypass permissions, and an auto mode gated by a transcript classifier. Safety is layered through pre-filtered deny rules, an ML-based auto classifier, hook interception, and optional shell sandboxing. Context management treats the window as the binding resource, using a 5-stage compaction pipeline budget reduction, snip, micro-compact, context collapse, and auto-compact plus lazy loading of cloud, MD instructions, and deferred tool schemas. Extensibility is split into 4 mechanisms with different context costs: MCP servers, plugins, skills, and hooks. Delegation uses isolated subagents with worktree or remote execution, sidechain transcripts, and summary-only returns. Persistence is mostly append-only JSON-L, and resume, fork intentionally, do not restore session scope permissions. Compared with OpenClaw's persistent gateway and perimeter-level access control, Claude Code is a repository-bound CLI harness with per-action safety evaluation. The paper's novel, forward-looking claim is that future agent systems should prioritize long-horizon human capability preservation because current architectures amplify short-term productivity without explicit mechanisms for sustained understanding or code-based coherence. Let's explore the third paper, Hierarchical Planning with Latent World Models. Hierarchical Planning with Latent World Models introduces HWM, an inference time hierarchical MPC abstraction for pre-trained latent world models trained only by next latent prediction with no reward supervision, skill learning, or goal condition policy training. The core idea is to couple two world models in a shared latent space, a low-level predictor for primitive actions and a higher-level predictor over learned latent macro actions extracted by a transformer action encoder from variable length action subsequences. High-level rollouts generate intermediate latent subgoals via latent state matching, which the low-level planner then reaches in a receding horizon loop. This structure reduces both compounding rollout error and action sequence search complexity. The paper reports up to 3 times less planning time compute and up to 4 times lower inference cost at matched or higher success. Empirically, HWM is plugged into 3 existing latent world model backbones: VJEPA2, AC on real Franca manipulation, DinoWM on push-T, and PLDM on diverse maze. HWM on real robot non-greedy pick and place from a single goal image. HWM raises success from 0% to 70% on cut pick and place and from 0% to 60% on box pick and place, while also reaching 70% on drawer manipulation, where the flat planner reaches only 30%. It outperforms Octo, Pi0, Fast, Droid, and Pi0, 5, Droid, despite those models using roughly 77 times more robotic interaction data. On push-T, success improves from 17% to 61% at 7.5 step horizon, and on diverse maze, from 44% to 83% on the hardest split. The gap widens with horizon, indicating better long horizon generalization. Ablations show latent macro actions are superior to delta pose abstractions, with action cosine similarity rising from 0.8 to 0.88, and that longer horizon high-level predictors outperform autoregressive low-level rollouts beyond about 1.5s. That's a wrap on today's AI paper highlights. Thanks for watching.